Hello, everybody, and thank you for this introduction. So this is a joint work with Jiehua and Rolf, and main part of this work was done when I was Humboldtian in Berlin. So let me start by recalling the classic stable metric model. We are given two disjoint sets of agents, U and W. And each agent from U has a strict preferences over the agents from W, and each agent from W has strict preferences over the agents from U. And it's also common to also consider models with weak preferences if we've truncated the ballots where the agents only rank the agents from the other side which are acceptable to them. However, most of our results extend to this model with weak and truncated ballots. Yet, for the sake of concreteness, let us focus on these strict preferences, since this is our main object of study. And in the classical model, we say we are looking for a matching where each agent from U is matched with some agent from W, and which satisfies the following notion of stability. For each pair of agents U and W, we would like that U prefers its matched partner to W, or W prefers its matched partner to U. Indeed, if such pair exists, and such pair would be usually in the literature called a blocking pair, then this pair would endanger the stability, since both U and W would have an incentive to break their relationships and to match together. And in our model, we also have two disjoint sets of agents U and W, but we enrich the model of preferences. So we now assume that there are L layers of preferences, and that each agent for each layer has possibly different ranking over the agents from the other sides. So in other words, we might think that we are given L different instances of matchings which share the same sets of agents U and W. And this new model of preferences, this richer model of preferences, also requires us to adapt the concept of stability. And our first finding is that there is actually not a single natural notion of stability, but we came up with three definitions. And all of these definitions actually extend the notion of stability in a sense that for a single layer, all of them boil down to the classical notion of stability. And in fact, actually, there are a couple of other mathematically natural notions in which this notion of stability can be extended to multiple layers. Yet we somehow selected these three as only for them we were able to find some natural interpretations and natural examples where they make sense and look reasonable. So the high-level idea is that each of these concepts of stability is parameterized with the value alpha, and intuitively this alpha value describes the strength of the stability. And intuitively, we say that a matching is alpha stable in multiple layers if it is stable in alpha out of layers. However, all these concepts differ with respect to the level of agreement that we require for the agents with respect to which alpha layers should we select and which layers should witness the stability. So our first concept is called global stability, and basically it says that a matching is alpha layer global stable if there exist alpha layers such that for each of these alpha layers the matching is stable, according to the classical setting. And a natural example where this concept makes sense is where the preferences of the agents depend on some external circumstances which are not known a priori. For instance, we can think that we are given a universe with several states. Each of these states is described by a single layer, and we are looking for a matching that will be stable in the largest number of layers. Then basically we are looking for a matching which is alpha globally stable for the highest value of alpha. And we can see that this is called global because these alpha layers that we require to witness stability is selected globally for all the agents. So our second concept is called pair stability, and we call a matching alpha layer pair stable if for each pair UW there exists alpha layers such that for each of these layers, either U prefers its match partner to W, or W prefers its match partner to U. And we can see that here, indeed, it's called pair because each of these alpha layer sets that witness stability is bounded with a pair. So it is selected, each pair must agree on a different set, possibly different set. And here the example where of an application where this concept makes sense is also when there are some external preferences, and the preferences of the agents, circumstances and the preferences of the agents depend on the context. Yet this context is pairwise specific. For example, when the when the women might have different preferences over men dependently on whether they agree to have kids or not, or whether dependently on which country they agree to live on, and so on and so forth. So basically, the pair agrees on some circumstances, and basically these circumstances form a witness for stability. And finally, the third concept is called individual stability, and we say that the matching is alpha layer individually stable if for each unmatched pair UW there is a subset of alpha layers such that either U prefers its matched partner to W in all of these layers, or W prefers its matched partner to U in all the layers. And maybe why it is called individual, maybe let me rephrase that a little bit. So we say that it's alpha layer individually stable if for each pair UW, either there exist alpha layers that U prefers W in these alpha layers to its matched partner to W in these alpha layers, or W prefers its matched partner to U in these alpha layers. So we see that these alpha layers are actually selected on the individual level. And the example where this makes sense to consider this notion of stability is, for instance, where each layer can describe certain criteria. And let's say in the matchmaking, this could be, let's say, intelligence, sense of humor, physical appearance, and possibly preferences of the agents are different dependently on this criterion. And we can say that an agent A will have an incentive to break her relationship with B and have an affair with C if and only if he or she prefers B to C. C to B in at least alpha layers. And if this is with this interpretation, then basically we are to have a stable relationship matching. We are looking for a matching which is alpha layer individually stable. So at first it might be tempting to think that these concepts form a hierarchy in their strength, but however their relation is a little bit more complex. Alpha pair stability is the weakest of these concepts. It is implied by global stability and individuality stability, which means that each matching which is individual stable is also alpha pair stable, and each which is globally stable is also pair stable. For different values of alpha, we can establish more accurate relationships. For instance, for alpha equal to L, alpha individual stability is the strongest notion, which implies global stability and pair stability, and global and pair stability they are equivalent. While for alpha equal to 1, the situation is quite different, and global stability is the strongest notion and implies individual stability and pair stability, which are equivalent in this case. So this was our first main contribution, that identifying like a conceptual contribution of identifying these notions of stability and exploring the relation between these concepts. And our second main contribution is in establishing computational complexity of finding matchings which are stable according to this concept. However, before I present these notions, let me also briefly say that recall the most important related work. In fact, our framework unifies and generalizes a few existing models. One of the models, one of the concepts is the concept of certain stability and possible stability. And actually, our concept of general stability for alpha equal to, for global stability, for alpha equal to L and 1 corresponds exactly to certain stability and possible stability respectively. People consider in the literature the model where the preferences of the agents can be intransitive. And in fact, our individual stability is quite closely related and might be viewed as an underlying model for intransitive preferences. So having individual stability, we can obtain intransitive preferences. So our analysis can be viewed as more fine-grained because dependently on the relation between parameters alpha and L, we can get some intransitive preferences or not, and we say for each of them how the computation complexity changes. And also, finally, let me say that there were some works on multi-layers in the late 90s. However, these models were very restricted, and for each agent, it was allowed only to have two preferences, which were exactly reverse. Okay. So this is the summary of our computational results. So let me say a few words about this table. So the first row is pretty obvious, and it is a consequence of the fact that all the stability concepts actually extend the classical concept of stability, and basically that the classical concept of stability can be solved efficiently by the Gale-Shapley algorithm. However, we can see that all of these other rows, almost all of these other rows, result in NP hardness. And actually, this is NP hardness for any fixed values of alpha and L which satisfy these inequalities. So even for two layers, the problem is already NP hard, except for this single island here, where we are looking for a matching which is stable, individually stable in all layers. However, we are also able to find some natural special cases which allow for a better tractability. And the first such a special case is which we call single layered. This means that preferences of agents on one side can be described by a single layer. And formally, we assume that there are multiple layers, but all of them are the same. And in this case, even in this case, these results, our results mostly speak about NP hardness. However, for some values of some combinations of the parameters alpha and L, we can get polynomial time solvability, or we can find algorithms which are efficient from the perspective of parameterized complexity. And finally, I think that this is the most interesting, actually, subdomain of uniform preferences. And we say the preferences here are uniform if for each layer, the preferences of all agents on one side are the same. And this intuitively corresponds to criteria which are objective. Right? So for instance, if we are matching students with the schools, then it is natural to expect that the schools will rank students basically only based on the ranks, on their grades. So each school will have the same ranking over the students. And in this case, actually, we have two nice open questions. And for individual stability, we are also able to establish a quite unexpected relation to the graph isomorphism problem. So let me now explain a little bit this relation to the graph isomorphism. So for any instance of a multi-layer matching problem, we construct two graphs. In the one graph, the nodes are the agents from the set U, and we construct this graph based on the preferences of the agents from W. And in particular, we create this edge from directed edge from U1 to U2 if each agent from W prefers U1 to U2 in at least L minus alpha plus 1 layers, right? So once again, we are in the uniform setting, which means that if at least one agent from W prefers U1 to U2 in this number of layers, then this is also the case for each other agent from W because their preferences are the same. And we do this the same for we analogously create edges between the nodes from W based on the preferences of the agents from U. And what's the property of such created graph? If we look at these four agents and we ask the questions whether U1 can be matched with W1 and U2 can be matched with W2, having this directed edge from U1 to U2 and W2 to W1, then the answer is that according to individual stability, it's not possible because this will be a blocking pair. Right? And now we can also observe that if alpha is greater than L half, roughly L half, then basically such constructed graphs will be tournaments. So this condition that such pairs cannot be matched can be also translated to saying that for each edge directed here, we can have exactly the same directed edge here from these two agents, which is basically exactly the condition for graph isomorphism, right? And now we can take advantage of, and we can use the algorithm for finding graph isomorphism between tournaments as a subroutine and obtain an algorithm which complexity roughly n to the power of log of n. Actually, a little bit more complex reduction sets also can be done also in a different direction without these restrictions on the values of alpha and L, saying that basically our individual stability in this model, in this uniform model, is at least as hard as graph isomorphism problem. Okay, to wrap up the discussion, in this paper we consider a new multi-layer model for and apply this model to the stable matching problem. We identified three natural concepts of stability, and we established the relation between these concepts. In general, finding matchings which are stable according to these concepts, except for like one single case, is NP hard. However, we also managed to find several islands of tractability for several restricted domains of agents' preferences. This is all from my side. Thank you.
I have one question. So is there, so all of these fairness notions are, stability notions are not always satisfiable, right? Is there a non-trivial notion that is always satisfiable no matter what preferences I get in all of these different layers?
Yeah, that's a good question. I think that unfortunately not, apart from the case of a single layer, which is basically the standard Gay-Shapley algorithm. If we go outside of this single layer, then basically in each non-trivial case we can find a counterexample where there exists no stable matching.
Right. So I was thinking of sort of something like, okay, so there would be probably a blocking pair, but if I like the outcome that you received on some alpha layers, then maybe you also like the outcome that I receive on some at least beta layers there. So that
I see. Yeah, this is an interesting question. Actually, I haven't thought about that. Yeah.